Let's look at radioactivity and the nucleus. Now, radioactivity is actually defined as the spontaneous emission of radiation from the nucleus of an atom. And this discovery of radiation actually allowed us to understand the structure of the atom, this spontaneous emission of radiation. It was discovered that some atomic nuclei are actually unstable, and because they're unstable, they emit radiation. Now, this emission of radiation is either called radioactivity, but it's also called radioactive decay. And it was this discovery of radioactivity or radioactive decay that helped us understand the model of the atom. Now, before we get into the model of the atom, let's look at some of the history of the model of the atom. And we've touched on this a little bit already. First of all, J.J. Thomson. He was the first to discover a subatomic particle, the negatively charged particle, the electron. And when he discovered this electron, he developed a model for the atom which was deemed the raisin bun, or the plum pudding model. And a raisin bun, if you're unfamiliar, they're not so popular anymore. You can also think of them as chocolate chip muffins. The positive was the bread, and the negative were the raisins. So Thomson's model looked like this. Most of the atom was positive, and there was these few little bits of negatively charged particles inside the atom. And that was the first accepted model of the atom. It wasn't until Ernest Rutherford came along and did his very famous gold foil experiment. And what the gold foil experiment is looks something like this. A piece of gold was pounded down very thin, and around it was a screen that would detect these alpha particles and these positively charged particles. And Rutherford wanted to find out what would happen if he struck this thin gold foil with these positively charged particles. And here's what he found. That these particles, most of them actually went straight through. Some were deflected, like they had been bent away, and others like they had struck a brick wall and bounced all the way back. Now this was confusing to Rutherford, because if we were going on the Thomson model and positively charged particles were being pushed through, you should get some sort of pattern, or maybe they wouldn't go through. The only thing that Rutherford could conclude that would give results that his experiment showed was that the Thomson model didn't work. The model of the atom actually changed. And based on Rutherford's experiments, where most of the positively charged particles just go straight through, some are bent and some bounce all the way back, what Rutherford was able to conclude was that the atom was mostly empty space. There wasn't much in the atom. And where the mass and where the positively charged particle was actually the center of the atom. And this is what he called the nucleus, this concentrated center of positively charged particles. And the model went from the raisin bun to a planetary model, much like the sun and the earth, or planets revolving around the sun, where in the center is this positively charged particle, and around it are these negatively orbiting electrons. And the planetary model was the model that held up for many, many years, and it wasn't until it was modified by our good friend Niels Bohr improved this Rutherford model. And rather than just saying these electrons are randomly floating around, the Bohr model states that the electrons are in specific orbits. And remember, we looked at these orbits, and these orbits fill up in certain numbers. They only can hold a certain number of electrons following that 2-8-8 model. And the Bohr model is still the model that we use today to explain simple atoms. Well, let's look at protons and neutrons. And it was actually Rutherford who identified that center mass, the nucleus, is the most basic subatomic particle, which is the positively charged proton. And for many years it was thought that the center contained just protons. It wasn't until James Chadwick did some more discoveries and found that inside that nucleus, there's also a neutral particle, which he called the neutron. What does this mean? Well, this tells us then that every single element has a different number of protons. And we did this through chemistry looking at the periodic table. Every single element is a different number of protons. Its mass is really made up of the protons and neutrons. And this now leads us to a standard new notation for writing a chemical symbol. On the top left would be the mass number, which is the number of protons and neutrons. And in the bottom left is the atomic number. The symbol just comes from the periodic table. And this is our notation for carbon-12. And this is the notation that we're going to use when we start writing isotopes. And an isotope occurs when an element has the same number of protons, the same atomic number, but has a different mass number. Now you might be thinking, well, if it has the same number of protons, how can it have a different mass number? Well, the protons are the same, but the number of neutrons are different. And neutron numbers are going to become very, very important. Different number of neutrons is going to result in a different isotope. When we're talking isotopes, these are elements that have the same chemical properties. So all the chemistry that we did previous, an isotope is going to have the same chemical properties. But because it has a different number of neutrons, it may have some different physical properties. Now, where have we already seen this, and actually have seen this, we just haven't told you yet, is let's look at carbon. Because we know that all carbon has 6 protons. Most of the carbon in the world, 99% of the carbon in the world, has 6 protons and 6 neutrons. And we call this carbon-12. Well, there's a very small percentage, less than 1%, that actually exists naturally with 7 neutrons. And if we add the protons and neutrons together, 6 and 7, we'll have 13, carbon-13. Now, a very, very, very small percentage, so small that we just call it trace amounts, actually have 8 neutrons. And we call this 8 neutron carbon-14. 6 protons plus 8 neutrons gives us 14. Now, carbon-14 is unique because it's actually a radioactive isotope. It will actually decay. And carbon-14 is actually formed when cosmic rays force these neutrons to bond in the center of the nucleus of carbon. Now, because it takes so much to bond, because it's so rare, carbon-14 is very, very small amount of the carbon. But if we look at this number, 12, 13, 14, and we did a calculation of the average, this is where we actually get the atomic mass on the periodic table. Adding up 12 plus 13 plus 14 and dividing by the percentage of carbon is going to give us the atomic mass. That's why on our periodic table we have numbers down here that actually have decimals. These strange decimal numbers down here actually come from the average of all the isotopes that exist. That's why we have those weird numbers at the bottom. And there are many different isotopes out there, including hydrogen. If we look at just hydrogen, 99.985% of hydrogen is just hydrogen, has 1 proton, no neutrons. There is a small percentage, about 0.015% of hydrogen, that actually contains 1 proton and 1 neutron. That's why the number at the top here would be a 2, and this is called deuterium. There is an actual radioactive isotope in hydrogen called tritium. And in tritium, we have 1 proton and 2 neutrons. That's how we get this number 3 up here. 1 proton and 2 neutrons. Tritium is actually radioactive, and it is in very, very small trace amounts. And tritium is actually used in nuclear power plants, and we're going to look at that as we get further on. Now that we have this new notation and standard atomic notation, what we want to do is understand this notation. So let's look at an example here. Imagine you are given the element uranium-238, and this number right here is the mass number. If we were writing this in our standard notation, uranium-238, the number at the top would be the mass number, and the number on the bottom is just the atomic number of uranium. Its number on the periodic table, which is 92. Now, based on this notation, we can actually find out the number of protons and neutrons. The number at the bottom, obviously, is the number of protons. And if 238 is the mass number, this number is the number of protons plus neutrons. So if we wanted to find the number of neutrons, it's just a simple calculation of 238 minus 92, and we get 146 neutrons. Just the top minus the bottom. Let's try another. Carbon-14. Carbon-14, we've already talked about that. There's our notation. Carbon-14, the 14 is the mass number. It goes on the top. This is the number of protons and neutrons. And the number at the bottom is just the number of protons. So if we wanted to find the number of protons and neutrons, well, protons on the bottom, simple calculation, 14 minus 6 to give us the number of neutrons, and we get 6 protons and 8 neutrons. And we're going to use this notation throughout the remainder of our course in radioactivity.